All right, and Naveed, you can start.
Okay. Yeah. So let's talk about CNNs today. CNNs stand for convolutional neural network. Um, they are very popular in computer vision for visual data. They excel at that. The idea, just like the normal neural networks, is also inspired from uh, biological neural networks. So, because lots of the visual system, like the visual system of mammals, work in a similar way, and because we can do experiments on animals, for that reason, we know a lot about how the visual system works. Um, and since we know that, um, what the researchers tried was to kind of mimic the same idea in a computer. So the way a visual system works is, when you look at something and you want to, when you are recognizing it, it's not like all the image comes at you at once. Your brain is accustomed to finding first the low-level features, so things like edges, smaller, maybe circles, eyes, and things, and they, on the subsequent steps, that they combine those to come up with a larger structure of it. And CNNs are kind of doing the same thing. So um, what they use are called these filters, and the filters, they look for, at the beginning layers, they look for low level features, and then at the subsequent layers they combine those to come up with higher level features, and then they finally are able to recognize the entire object. Now, before I begin talking about what a CNN is, let's first talk about why a simple neural network, the multi-layer perceptron that we talked about previously, wouldn't work. What kind of limitations do we have in there? Um, Let me share my screen. So, because of the accessibility of us doing experiments on animals, um, there's a lot of it is known for computer vision, and that's why CNNs are very successful. And there's no doubt, when it comes to, like, there's people from non-AI people and AI people both that don't quarrel much about how CNNs work. But when it comes to language, there's a huge discrepancy between what people, what AI people think it is doing and what non-AI people think what it is doing, for the simple reason that language is unique to humans, or the sort of language that we use is unique to us. And because we cannot do experiments on humans, that's why there's a big, um, I mean, the the AI people think that it is doing something very similar to what humans are doing, and the non-AI people, people like Noam Chomsky, who's a famous linguist, they think that this is just simply searching astronomical amounts of data to find patterns, and then that's what it is doing.
Yeah.
The example that he usually gives is, it's like, you are saying, can a submarine swim, or can an airplane fly? He says if you want to call that swimming or flying, that's up to you, but at least I don't think it swims. So it's just kind of mimicking the same behavior, but it's nothing what a human brain is doing. Anyways, so let's say we have a picture, and just like, you know that a picture is nothing but a bunch of pixel intensity values. The problem, so suppose we want to recognize what's inside this picture. How can we present this data to a neural network? Well, what we can simply do is take these pixels and stack them into one long vector, and then we can just simply feed that directly to a neural network. And if you remember, a neural network is nothing but a bunch of logistic units stacked on top of each other. So you can connect these pixel intensity values to these individual neurons with different set of weights. So these would be one set of weights, and then for the second neuron, it would be a different set of weights, and so on. Now, if you carefully look at it, there are lots of connections. There are going to be uh, formed as you connect these this input data. For instance, this picture is a, let's say, 1,000 by 1,000 pixels picture, and the result would be 1,000 squared. And then suppose you have, let's say, 128 hidden units in this first hidden layer. Now just imagine for a second you have to connect those 1,000 squares to 128 neurons with different set of weights. So you can simply see the weights of this model just rises very quickly and to huge amounts, and the result is a gigantic amount of learnable weights that you would have to train. So that's one problem with this traditional multi-layer perceptron. Uh, Multi-layer perceptron, dense layer, fully connected layer, all of them just simply refers to the same simple neural network that we talked about. So that's one problem with it, that the learnable parameter size just quickly grows. Second problem is the way this neural network is learning from this image is, suppose the task was to do cats versus dogs classification, and suppose the cat was appearing at the upper left corner of this image. When you stack these pixel intensity values on top of each other, those cat pixels might appear here. And let's say we train this neural network, and at the end, this recognizes that it's a cat. This would only recognize that it's a cat based on the fact that this cat is sitting at the top left corner. But if you then change the position of this cat, let's say this cat then appears at this position, this neural network would be unable to recognize this thing because now you have changed the space of the cat, and because that special information is embedded into this neural network, it's not spatially invariant. It does take care of of where that object of interest appears. And for that reason, even though it's the same cat and we would like the output to, like, once it learns from this image that that a cat looks like this, we would like this neural network to behave in a way that even if we change the position of this cat, it should not impact the, the output decision of this neural network. But for a fully connected layer, because it doesn't take care of that thing, it's not spatially invariant. That's why it would be difficult for it then to recognize that it's a cat if you change its position slightly. Does this make sense?
Yeah, yeah, this is actually what I've been thinking about for a long time, because even if you move it like just slightly, then a pixel that might have been like black before is now like a different color, like
Exactly.
lighter or darker, and then it all shifts. Yeah.
Yeah. So that's exactly the phenomena that occurs. Now, if you just simply think for a second, how could we mitigate this issue, this special invariance? How can we introduce special invariance into this thing? An ideal, or like what I think is would be intuitively a good idea, is that we can somehow fetch this cat features from this image, and then train this neural network based on that, rather than taking these pixel intensity values directly. So if you can somehow fetch this information of a cat or whatever your object of interest is, it would become a lot easier for this neural network to then to recognize what a cat looks like. And even if you then change its position, because it would be looking for cat's features and it would be ignoring the rest of the background that appears, that problem would solve. And this is exactly what a convolutional neural network um, is trying to achieve. So the term convolution, it comes from signal processing. I'm not sure if you are familiar with with linear systems. The way the way we compute the output of a linear system is we have what is called an impulse response of the system. So an impulse response just simply means that you have this system, and you know what would happen if I pass a single sample from the system. If we know the output of this system to a single sample, we can then compute the output of this system to any signal, because we can take any signal and then um, transform it into these samples, and because we have we know the response to a single sample, we can combine the responses to each of these individual samples, and this would give us an output for that system. But we can only do this for the kind of systems which are both linear and time invariant. So we do this for what is called LTI systems, which are both linear and time invariant. And the way we compute an output for such a system is we can do that using convolutions.
Naveed,
So,
can you give an example?
uh-huh.
Could you give an example of such a system?
Okay. An example of such a system. Well, suppose, well, I have to open my signal processing book for it, but um, systems which are not non-linear, so they don't involve these terms,
Yeah,
high order terms, and also they don't change with time. So, for instance, if you feed this sample at one time and the response that it provides you, and then you feed the same signal at some other time,
yeah,
time t plus 1 or t plus 2, at that second time, the response is the same. This is called time invariance, that with the flow of time, the response of that system doesn't change. So if the system has these two properties, then it is an LTI system. Um,
so it's a very simple
you
system.
can, yeah, it's a very simple system. You can think of it like that. I know it would not make any practical sense, but a system which, let's say, just simply adds something to a signal. So let's say just simply does x plus 2, or something like that. It may be, it
So
does something.
I'm looking at some examples. So it's like if you
Mhm.
have like a circuit where you have
And
like
an amplifier could also be an example where it just simply increases the volume or the amplitude of something. That could also be an example of an LTI system.
right. So like or a water heater where you put in more heat and the water that comes out is hotter.
It could be, but I'm not really sure
But
about that.
but, but I'm guessing that if there's a delay, if there's like delay factors in it, then that would make it not time invariant, right?
Yeah, so if a system involves terms like, let's say, x into sine t,
Yeah.
then it's not a time invariant system, because with changing time, this sine factor would provide you something that would be different at one time, and at the second time it would be different.
Okay.
So it's not a time invariant system. Systems which are linear and time invariant, you can compute their output uh, just by knowing their impulse response. All of what I'm saying is literally have nothing to do with convolutional neural networks. It was just to tell you that we can, the term comes from there. We use convolutions to compute the output of a system for which we have this impulse response. How do we do it for images? If you, so like the the if you have what is called a system, it could be a filter. A filter is just a system which modifies your signal in some way. um, we can compute the output of a filter to a signal, which could be an image, using what is called convolution. So let's take a look at an example of how do we compute the convolution. How do we compute the output if we have a filter and we have an image, which is a signal? How do we compute its output? We do it using convolution. Let's see how convolution works. And then we'll also talk about what this particular filter here is doing. Felix, you with me till now, right?
Yeah.
Great. So we have this filter. Filter is nothing but just a bunch of a square. You can think of it as square matrix. So here you see a 3 by 3 filter. 3 by 3 just simply means you have 3 rows and 3 columns. And here we are just simply taking a simple image, which is a 6 by 6 image. The left side of this is contains pixel intensity values which are 10. The right side are just pixel intensity values 0. And if you look how this image would appear, if you plot it um, using Python, you'd see this side to be a white strip and this side to be a black strip. So the way we compute convolution, the output, like what would happen to this image if we pass it from this filter is, we take this filter, we place it on top of this image. let's say this green rectangle, this green portion that you see, we just simply take this and place it on top of it, and then we just compute the dot wise multiplication. So the point multiplication. So we take this 1 multiplied with 10, take the 0 multiplied with 10, negative 1 with 10, and so on. This one with this 10, and for the rest of them. And then we just simply sum all of them together. And once we sum them, that's how we produce a single output. And then we shift this one place towards the right, which would then be placed on top of this. And then we again do the pointwise multiplication and again do the addition. And that's how it would generate this second pixel. For this example that you see, because he has shifted this, like how would you compute in the third one? You just simply shift it two places at a time, and then again compute the dotwise multiplication, and that's how it generates the third and fourth, and then you shift it one place down to generate this one, and so on. So this red one that you see, it would be computed by placing this filter here on top of this region and computing the dotwise multiplication, and then that's how it would generate this output. This process is clear, right?
Yes. So you're basically reducing the complexity somehow, right? To
Yeah.
detect
So
the
so
edge.
so let's talk about what this filter is doing. But you are clear about the computation, and that's literally what a convolution is doing. This
Yeah.
is called a convolution. So let's see what is this. What is filter doing to this image? This filter is called a vertical edge detector, as you can see here written on top. So when you have this white region and this black region, at the middle you can see it forms an edge. As you shift from a white region to a black region, an edge is forming there, right? And we are calling it a vertical edge detector. Now, if you plot this thing that is generated as an output, you see that the left side of this is black, the right side of this is black, and in the middle you see a white strip. So in other words, it's highlighting that edge which was at the middle of the image, and it's darkening the rest of the image. So it's literally hiding the rest of the image and only highlighting regions where there's an vertical edge forming. Does this make sense?
Yep.
So yeah, so this is what this filter is doing. Now if you rotate these numbers 90 degrees, this negative one would appear on the top and this positive ones would appear on the down on the bottom, and then the zeros would be in the middle, and that would then form what is called a horizontal edge detector. And then if you compute its output using the same convolution phenomena that we described, the output, if you plot it, would then highlight the vertical edges. Now, since in this case we don't have any, sorry, horizontal edges, so we don't have any horizontal edge, there would be, most of the pixels would be darkened. But if you have an image which does contain horizontal edges, that filter would then highlight the horizontal edges. And similarly, as you can see, this, because we have negative ones on the right side and positive ones on the left side, this filter is not just looking for edges, it's looking for vertical edges, which are forming by going from the white region towards the darker region. If you shift this negative signs towards this side, it would be then looking for vertical edges, which would be going from darker to whiter regions. So the point to take away here is, by manipulating these numbers here in this filter, you can come up with different filters which would be looking for different features. This particular filter is looking for vertical edges, but if you change these numbers, it could be looking for some other kind of features, and those features wouldn't even make sense to you. Like, it could be looking for something that doesn't make sense to us, but that would be still somehow valuable in some ways. So convolutional neural networks make use of these filters. The question is, um, how like how do we come up with what features should it be looking for, right? That's the question. And the answer to this is, we don't have to. We can literally treat these numbers as learnable parameters, and we can uh, shift this task from ourselves to the training of the neural network, where it has to look for whatever kind of filters would be useful to it. The only thing that we want from it is to do, let's say, the final task that we have that we're interested in, which could be, let's say, image classification, and then we can just simply throw them a bunch of filters um, with randomly initialized values, and as the process, as a result of the process of training, it can come up with whatever filters or whatever features that would be interesting to it, which would help it do the the task, which could be image classification. Does this make sense?
It makes sense. I'm just wondering what happens when those features get more complex, right? Because this is an easy example and it makes a lot of sense.
Yeah.
Hmm.
So you're right. The 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 more complexity you have in your picture, the more it would be difficult for you to handcraft features, and that's why I said, like, we don't have to worry about that. So it would not make sense to you. Even like if you go, James would show you in the code. He would be plotting these these intermediate outputs of the filters. These are usually called the feature maps. So if you have an image, you convolve it with a filter. The output is a feature map. You call it a feature map. So even if you visualize those feature maps, uh, it would hardly make any sense to you, but still it would be useful for the neural network. So since we don't have to worry about handcrafting these filters, that's why we don't need to worry about what features would be important for it. This example that I gave you, that it could be doing vertical edge detection, this is just one possibility that is out there for this filter, but there could be thousands of other things, just like I said, which wouldn't make even sense to us, but that would still be useful for it. So let's see how this is solving the problem that we talked about in the beginning, which was the first one was astronomical amounts of parameters. So let's see if you would have fed this image directly to a neural network, how many um, linear parameters would be there. So suppose you had um, if you just had a single hidden unit, you would have to train 36. You'd have to train 36 um, weights. And if, let's say, you have 128 hidden units, then you just simply multiply 36 with 128. But in this case, you just have these 9 trainable parameters. So it is drastically reducing the amount of parameters, learnable parameters, that you would have to train. And the second thing that it is doing is this filter acts as a feature extractor. So it doesn't really matter where the cat appears now. If it appears in the upper left corner or in the upper right corner or in the bottom corner, once you pass this image from this filter, it has greatly reduced that. Um, it is now fetching the features from it, and in the subsequent layers, like this feature map, you don't directly then feed it to a neural network. You apply a second set of filters and a second layer of convolution, and that even further reduces the spatial information. In other words, it is kind of deleting the spatial information and only fetching the relevant features that we are interested in. So that's how it is. It is making this process spatial invariant, or the term is called spatial invariance. So that's how it is kind of achieving that goal as well. Does that make sense?
Mm-hmm.
Okay. So this is the backbone of convolutional neural networks. The rest of them are just some slight implementation details. One of it is called pairing. So what is pairing and why do we do it? Pairing, as just simply its name suggests, is suppose if you look at these center pixels here, let's say this 10 and these zeros, um, when you shift the convolution filter and place it on top of this region, these regions appear in one pass of it, and then when you shift it towards one place to the right, the same region appears once again. And if you shift it even once further, this region even appears once again. The point that I'm trying to tell here is the center pixels appear more and more in multiple convolutional steps. But if you look at these corners, edges, they just appear once when you are doing the convolution. So when you place this filter on top of the upper left corner, this region appears only once, and then that's gone when the filter is shifted one place at a time. And for that reason, features which appear in the edges of this picture doesn't kind of get more, those features are kind of faded away because they appear only once in the convolution operation. In order to prevent it from doing that, in order to highlight the edges as well, what we do is we introduce an extra padding layer, which could be, you can pad it with two extra layers or you can pad it with one extra layer. And those padding are just simple introducing zeros on all four corners of it. So you just simply add one extra edge here, all zeros, one here, all zeros, and here and here. And that way you can highlight the edges of this image as well when you're doing the convolution operation. And this is called padding. Does it make sense?
Yeah.
Okay. One other important step in a convolutional neural network is called pooling. So the pooling operation, um, as you'll see, we don't just make use of a single filter when we are doing convolution. We can literally, it's a hyperparameter, so you can throw, let's say, 64 filters or 128 or 256, and the number just simply keeps on increasing as much as you want. But the result is, let's say if you have 128 filters here, you will have 128 feature maps at the output, because each of the filter would be looking for its own feature map. So maybe one filter is looking for vertical edges, another would be looking for horizontal edges, and you have 128 of them, and the result is 128. So this 4 by 4 would be 4 by 4 by 128, where 128 would be the amount of feature maps you have. And as you can quickly see that this output, um, the data, the output space is just keeps on increasing. In order to prevent it from growing too much, what we do is called, what we do, which is called pooling, is we can squeeze certain chunks of the output image to a reduced number of pixels. So suppose we can take this upper left corner 0, 30, and 0, 30, and we can replace it by just one pixel, which could be either the average of these four, or it could be either the maximum of them. So a particular type of pooling, which is called max pooling, just simply takes these four uh, numbers and replace them with the maximum, where the maximum here is 30, but it's just a simple example. The real example would have something else where there would be one maximum and the other would be lower than that. So what it is achieving is it is reducing this output feature space. Its size is reduced. So if you make this one pixel and this one pixel and this, the 4 by 4 would then shrink to 2 by 2, and that's how you reduce this output, the size of the feature map. Now, of course, you are losing some information when you replace these 4 pixels with just one, but it turns out that if you do it, the output feature space is reduced, and the information that is lost is not that much. Like it it kind of the performance of the algorithm even further improves with it. A possible justification for it could be because you're replacing this with the maximum number. Whatever feature it was looking for would even be further highlighted, because you are taking 4 pixels and just replacing it with the maximum one, and the maximum one would just simply intensify further whatever feature that you were looking for. But this is just one justification for it. Of course, it was just shown that if you do pooling, the performance of the algorithm increases and the computational requirements are reduced. But usually a convolutional layer is quickly followed by a max pooling layer. You can even skip max pooling, but if you do it, sometimes it helps. So people sometimes include the pooling operation. Does it make sense?
Yep.
Okay. One final thing, which is called the stride. The stride is just simply how much you shift this filter when you are computing one pixel at the output. So the example that I described here was just simply using the stride of 1, which just simply meant that we took this filter, placed it on top of this region, and then we shifted one one place at a time to compute the second pixel of the feature map, and so on. In this case, the the stride was 1, but you can even increase the stride number. So you can make the stride equal to 2, in which case you would be taking this filter. Once you compute the output for this region, you would shift it 2 places at a time, and not just one place at a time. So the second pixel would be then this region um, that you would be placing this filter on, and so on. So why do we do? What could be the reason for increased stride? The simple reason is that it reduces the output dimension of the feature map. So if you have, like, let's say the image is too big, it's 1,000 by 1,000 image, and you are also making use of lots of filters, this could be increasing the output dimension, the amount of output features that you're getting. In order to prevent it from doing that, you can just simply increase the stride number. So things like stride and pooling, both of them are used to somehow have some controllability over reducing the feature space that your convolutional filters are doing. And that's called stride. And that's literally all about a convolutional neural network. So once you compute these convolutions, you can then simply feed them to a dense layer, which is the simple neural network. So suppose we have this image, we can apply um one layer of convolution filters. So I'm just calling it simply filters one, and then you can combine another convolutional layer, filters two, and you can, let's say, have more than one filters here. So you can, let's say, have 64 filters here, you can have 128 filters here, and so on. So let's say the initial image dimension was 6 by 6. By the time you apply this, the first convolutional filter, the output could be, let's say, 4 by 4 by 64. And the time you apply the second filter on it, at that time, let's say we are making use of the filter size, which is reducing this 4 by 4 to, let's say, a 2 by 2. It could be 2 by 2 by 128. And then you can directly apply this to the output layer, where, let's say, we were doing cats versus dog classification. So it could be a simple neuron here, the perceptron that we talked about, and we could apply the sigmoid activation function on it, which would be computing the probability if it's a 0 or a 1. And that's how you can classify it. Or you can also apply one dense layer before you feed it, or two dense layers. That's literally up to you. So before you apply this to the output layer, you can feed this to a dense layer. How do we feed it? We again do the same operation that I described in the beginning. We just simply stack this into one long vector. So this 2 by 2 by 128 just simply is stacked into one long vector, and then that vector you can feed it to a dense layer and to the output layer, or you can also skip this dense layer and directly feed it to the output layer. Does this make sense?
Naveed, there's one thing that also kind of tripped me up last time here. So with the output of the first convolutional layer, you obviously have 4 by 4 because that's the size of the feature map, right? The 4 by
Mm-hmm.
4. And then you have 64 because there were 64 filters.
Mm-hmm.
You go to the next layer, you have sort of 64, almost like 64 different feature maps that you need to
Yep.
apply 128 filters to. So
Yeah.
then do you end up with 64 times 128 feature maps after that? Or
Yeah.
or how
Yeah.
does
So what happens is, so how would you apply a filter to this thing? So the way you do it is, we have 4 by 4 and we have 64. So this is literally like the depth of those
yeah.
4 by. So you have one feature map, and then there's a second one and a third one, and so on. How would a filter be applied to this thing? Now, if I want to apply a second filter to this thing, I would have 64 channels of that filter. So let's say my filter is a 2 by 2 filter. This 2 by 2 filter would need to have 64 of 64 of them, and then
Oh,
you apply this to the first one, that to the second one, that to the third one, and the output is literally just the sum of all of those. So this pixel value gets multiplied to that one, this multiplies to this one, this is to this one, and that to this one. I'm assuming that we have a 2 by 2 here, but the, the convolution operation stays the same. If you want to compute one output pixel, you just simply have to take this filter, place it on upper left corner, compute the dot-wise multiplication, and you do this for the second feature map in the same way. So you take the second, you can say, the portion of the filter, place it on top of those four, and that one to that one, and so on. And then you just simply aggregate all of them together to compute one pixel of the output feature map. This is just for one filter. You do it for 128 filters. Does this make sense?
Yeah. So for each filter, it needs to have
For
this number of channels as the number
yeah,
of filters in the last layer.
exactly. For each feature map, you need to have that filter, which would correspond to that feature map. I mean, describing it is confusing, but I hope you get the idea.
Basically, all of the matrices need to just have the right number of
Exactly,
dimensions.
exactly. You,
Yeah.
you just have to make sure that you have 64 of them um, for each of 128 filters. So like if you take one filter from it, it would have 64 channels just to match this feature map, which are 64 in the last layer.
Okay.
Okay, and that's all from my side.
Great.
Just one thing which I skipped throughout was that you also apply a nonlinearity on the outputs. So once you take this filter, place it on top of this, and compute this one pixel at a time, you sum them all together, but you also apply that nonlinearity, which is typically a ReLU activation. So you apply that, and then you place it here. For this example, we didn't do it, but for a practical neural network, you also apply that nonlinearity on the outputs.
Mm. Okay. Got it. All right, Felix, are you ready to see some code?
Sure.
Not tired out?
I'm all right.
Perfect. Well, so the last thing that we did was we coded our own neural networks using simple data sets like the housing data set. And yeah, now we're going to train our own convolutional neural networks using image data sets. So this is the example project that we have here. And so basically the idea of this project is that you can take any data set that has different images, and those images should be labeled into different categories. Ideally, for the simplest project, you just have two different categories, but it's actually possible to make it work. And I kind of put it in here. It's actually possible to make it work if you have more than two categories as well, if you want to. So these are just some that I found, but really, it's probably more fun if you find your own. Um, and yeah, this is the code for a convolutional neural network. So a lot of this stuff is going to be the same as what we've done in the um, feed forward neural network. However, we have a couple of new things here. Do you see that? So we have now a convolutional layer that we're importing from Keras, flattening layer, and then we have the max pooling, which is all stuff that we've just talked about. Oops, that's not what I wanted. And there's also just a couple of functions for pre-processing with images. But this is the most of the new stuff that we're adding today from the regular neural network. So the first thing that I did in this is I downloaded the cats and dogs data set, and you won't be able to see it here. I could run it again, and then what that will do is that will download a big zip file with images that are just put into different folders by cats and dogs, and then this command will unzip that if I import all of the libraries I need to import. And I'm not going to run this whole notebook because it takes a bit of time to train the network, but I want to show what the actual file structure looks like, because that's kind of like can trip you up when you're training. So here they have like a training and a validation folder. which is looking at the training folder, and then they have cats and dogs. So if you have a data set, and then a lot of pictures of cats and dogs. And so if you have a data set which is in this file structure, then you're perfect. You're ready to go. Otherwise, you can also find another way to label the data, but this works really well. So this here is just parsing through that file structure and counting the number of images in each folder. There's nothing special here. It's literally just looping through all the images, and as you can see, we got a bunch of different images of cats and dogs from different angles, and there's a lot of variety in here, so it should create a pretty robust classifier. And here, this is the core of what we're doing today. We have defined a sequential model, just like we did in our regular neural network. But the difference is, before we get to these dense layers, we've added one convolutional layer, the max pooling layer, which I'm sure you remember. And then this flattening, all that does is it takes your what you have, which is a matrix, of many values, and then it just flattens that into a one-dimensional vector. So it just puts everything in a sequential order. It's the same data, but in a different size. And that's necessary to get to the neural network layers, which are flat. We've used ReLU before, and I think we've also used the sigmoid before, or at least the sigmoid is very similar to what we did in our second lesson where we were doing classification. But the main thing to realize here is that whatever gets put from this second to last layer into the output layer results in one final output that ranges from 0 to 1. And so then from there, we just have to set a threshold determining what's the threshold where it becomes a cat versus dog, maybe 0.5, maybe something else. This convolutional layer, it has a bunch of numbers getting put in here, so we should just go over what each of those numbers mean. So we have here the number of filters, as you can see, is 16. The kernel size, so that should be the size of the filters, 3 by 3. Activation function, as you know. Did you want to add something?
No.
Okay.
3 by 3 is just the filter size.
Yeah.
If you even just simply put one 3 there, it would still work. It would automatically know that it's a square filter.
Cool.
By 3 by 3.
That's good to know. And then for the input shape is of course the shape of the image, and once you train your network using this input shape, you can't just change. You cannot change the input size without retraining. So you have to basically resize all the images that we feed into the network to make sure that they are these dimensions.
So the images in the data set are already in this format?
They will
because
be.
They have different shapes, right?
Yeah. So looking here, they're not all.
Yeah.
You can already tell they're not all square images. So
Right.
they will be transformed before training and before testing. Yeah.
Automatically.
So there's some helper functions basically that help us to do that. It's not the beautiful part of the code. It's basically just pre-processing. And we're about to do that one too. So as you can see, this is the network we just set up, and for yours, you probably you might want to do something a little bit more sophisticated than this. I've just done one layer and then one max pooling layer, but that is just the simplest possible model.
And
So
the phenomena that I was describing, the feature, the learnable parameters. If you look at the convolution layer, we just have to train 448 parameters. But then if you compare it with the dense layer, that number just quickly grows. That's because we have to connect every single pixel to every single neuron.
yeah,
That's why it's called fully connected layers. So you can see that in here as well.
yeah, and you can see, as I mentioned before, like if this is 74 by 74 times 16. If we multiply those together, then we get this for the platen layer. And I guess if you take that times 64 and then add 64 for the biases, then you get
Yep, you'll
this.
get that.
I hope that makes sense. So the when we compile, then you're choosing the loss function. Now, Naveed and I were just talking about this last week, but the binary cross entropy here, it goes with this sigmoid function. Um, and if we would choose a different, so in this sigmoid function, as you can imagine, that's only for two, if you have two categories. I don't know if we want to go too deep into this right now, but if you have more categories, you can use what's called the softmax function, where basically instead of one number, it'll give it, like if you have three categories, it'll give three numbers, and then all three of those will add up to one. So for example, if it's 50% sure that it's a cat, then it would give like a 0.5 for that. And if we would use that as the output function, then you would use a different one. That would be the sparse cross entropy, right, Naveed?
Yeah, to quickly summarize this thing, so if you are doing binary classification, the good thing would be to use a sigmoid as an output at the last layer of the network with a single neuron in there, just like here. But if it's a multi-class classification problem, suppose you have three or more than three classes, in that case, you just simply need to match the output neurons to the number of classes that you have. So if you have three classes, you'll put a 3 in there in the last dense layer, and the activation function should be softmax. Why softmax? Softmax just simply makes sure that at the output, we convert those activations into probabilities, and it makes sure that if you sum up all the probabilities of the three classes, they should add up to one, in order to just simply match the principle of probability that all probabilities should add up to one. So if you have three classes, the probabilities could be distributed in a way that first class could be getting a probability of 0.7, and the second could be getting a probability of 0.15, and the third one of 0.15. And then to make a decision, you can just simply pick the class with the maximum probability. So that would be for multi-class classification. And the distinction between sparse and just categorical cross entropy, I think that is, we don't have to go into that. That might, like, we don't need to go into details of that. But if you transform the output labels into one hot encoded version, you don't need the sparse keyword with it. But if you don't transform them, and then the output is in the similar format, like if you have three classes, for class 1 you have a label of 1, for class 2 you have a label of 2, for class 3 you have a label of 3. In that case, you would need to use the sparse keyword with it, just to make identify this to the network that our output labels are not one hot encoded.
Cool. Yep. It ends up being quite simple when you code it up. Cool. Then the next thing that we do is exactly as you said before. So going to rescale all the images to one to the right scale that we want.
Yeah, we just simply multiply with 1 divided by
Oh,
255, which is, in simple words, just dividing every single pixel with 255 to normalize them. And why do
oh,
we do normalization? If you remember, well, we simply need to make sure that every single pixel varies between 0 and 1 for numerical stability and to prevent biases and stuff.
yeah. Okay, so this is scaling the pixels from 0 to 1, and then
Yeah,
for scaling the actual images, that's actually done from this generator function, which we don't even look into. So we just set the target size of the images that we want, and then that will rescale them.
Yeah, so a good thing about the image, so we are using image data generator here, which comes with TensorFlow. The good thing about it is, if you would like, if you suppose don't want to use an image data generator, in that case, you would be storing every single image in, let's say, a NumPy array, and the target variables would then have to, so like xtrend would contain, let's say, the pixels of the images, and the ytrend would contain the corresponding labels for those images. So you can do that, but the problem with it would be all the data would be then stored in your RAM, which could overflow it if you have a gigantic amount of data. The image data generator, what it does is it efficiently handles large amounts of data. So you declare an image data generator, just like here in the code. You can specify some operations that you'd like to perform. So here we are just simply doing rescaling by dividing it by 255. But you can also specify some other operations here. Suppose if you want to do image augmentation, where in augmentation we just simply take an image and do some variations on it in order to increase the amount of data that we have, horizontally flip it, maybe rotate it, and things like those. You can also declare them in the image data generator. And then you just simply specify where the images are coming from. So in the lines below, where we have flow from directory, we just simply specify the directory where the images are stored, which is train directory here. The batch size, which it would just simply bunch um, every single, like it would create these chunks of 16 from the data. And then the class mode binary just simply specifies to it that we are handling a binary classification problem, and the target size is, you just simply need to resize every single image to that size. Now, as you can see, we are not specifying to it what is the label here. It automatically fetches it from the directory itself. So if you look at the left side of the screen, we have cats and dogs filtered. James, can you open up the train folder? Yeah, as you can see, we have cats and dogs here. So it automatically knows that I have two classes here, one cats, one dogs. Cats images are in the cats folder, dogs images in the dogs folder. And that label information it fetches from the directory itself. So all we need to do now is to just simply feed the model.fit function with the train generator, and it knows that we have images in there, and those pertain to two different classes, and
Yeah.
that's how it simply fetches images and trains the model on it.
Yeah. So yeah, the next step is to actually train the model, and yeah, there's a batch size which just determines how many basically how many images can be passed in at once. Is that a good way to describe it?
Yeah, so batch size, just we don't simply take the entire images and do the gradient descent on all of them together. We do this on chunks, and that chunk is what is batch size. So we run the model on 16 images, it creates an output, we compute the loss, and then we take the gradient of that loss and then update the weights for 16 images at a time.
Right.
And we do this again and again. And because we are making use of GPUs, we can do this in parallel. So we can take our 2000 images, divide them into, let's say, 16 batches, which could, so if you see this epoch here, this 1 by 15, this 15 is actually, James, can you scroll it to the left? So this
Uh,
15 is, yeah, so this 15 is the total number of epochs. But if you see there is 125 divided by 125, this 125 is the total number of batches that you have. So if you take your original images, which are I think 2000, and you divide it with 16, you will
Yeah.
have 125 of them. So 125 is the number of batches that you have. And then you can just simply take batches and spread them on multiple threads of GPUs, where each would in parallel kind of compute the gradients and update them, and then you can aggregate all of them together to have this combined effect.
Okay, so if you have enough power in your GPU, then it will actually run 125 batches at the same time.
Yeah, and if you increase the batch size, so like let's say if you increase, yeah, so if you have lots of images, and let's say right now you're using GPU T4 GPU, and if you keep on increasing this, let's say make it 64 and then 128, at one time the collab would throw an error saying that the GPU doesn't have that much memory. In other words, it cannot take that number of images and place it in the RAM of GPU. Maybe you can then go towards higher end GPUs like 100, which does have the memory size. But if you don't, then you'd have to reduce the bit size in order to match it the amount of RAM that you have on your GPU.
Great. So we can see the loss and the accuracy here, but it would be just easier if we will just plot them actually. So I believe I haven't plotted it.
Oh,
Oh, we could plot it, but if we look here, we see that the accuracy of the training set comes to actually 100, but the real accuracy with the test set comes
and
to
Felix, can you tell us what is this phenomenon called?
this.
Sorry, I was on mute. Overfitting? Is it overfitting?
Exactly.
You got
What
it.
is overfitting?
$1 million, Felix.
I'll come pick it up.
So so then we do the same thing that we were just doing here with the validation accuracy. We can run that again, just to show you how to do it as a separate function. These are the classes that it's been that the model class categorizes into. Now, I wanted to just take an image of a dog from real life that I had, and I wanted to test the model on that to sort of see, okay, how does it apply to a dog that I know? And so this is just downloading one from my Google Photos collection, and so this is the dog um, from back home in New Hampshire, and his name is Bamza, and the model has classified it as a cat. So I think there's like some different possible explanations for that. Could you think of any?
What are you asking?
Felix. Well, of course, we already know that the model is only 70% accurate. However, can we think of like anything here that might cause it to classify this one as a cat?
I mean, there's many reasons, but maybe in the training set, the cats are primarily like this color or in
Yeah.
a certain pose or something like that. Yeah.
Yeah. What do you think, Naveed?
What I think is this is an unusual picture.
Yeah.
The tongue of the dog is sticking, and then and we are only seeing its face, not
Yeah.
the entire body.
Yes.
So maybe that could be the reason.
Those are exactly those are my two exact hypotheses. If only there was a way that we could test this, so we could sort of learn more about what the model is doing. Well, hey, what if we would actually draw out those feature maps that are the output of the convolutional layer?
Have you done that?
Sorry?
Have you plotted the feature maps?
And here's all the code that we won't
Oh,
need to go through that does that. And then here
great.
are the feature maps. So this will sort of help us to do some detective work. And of course, we don't really know what's happening here ever. But the first thing I did was kind of to see, oh, does it like, is it looking at the tongue? You know, are there any layers that are detecting the tongue? And actually, there's
The
not.
tongue is the tongue is completely missing.
There's nothing that highlights the tongue. However, there is a lot of focus on the chin. You know, the shape of this bottom of his face is almost everywhere. You know, so
Yeah.
that leads me to think it's not really, because we haven't outlined the whole dog in this image. It's not really looking at the outline of the dog. It's mainly looking at the outline of this face here. It probably thinks that this black here is actually a background, you know?
Yeah.
So that was pretty. Oh, let me. Probably thinks that this black here, this black fur of the dog is the background. It's just looking at this little face here, and that's probably where the confusion arises.
There's also another
Interesting.
way to visualize what the model is doing. The technique is called grid chem. I'm forgetting the name, but it would be better, James, if next time you also
Uh huh.
you show that thing. So what it does is
Yeah.
it goes to the internal layers and it computes the gradients of the, I think, of the filters themselves, which then highlights. I think this is what I'm referring to. So it further highlights what particular region of the image the model was paying attention to as it was describing or as it was making its decision. So grid came kind of further highlights this thing. Maybe we'll come up with the code next time.
Right. That makes sense because we've plotted just the convolutional part, but then later on, those features get detected by the neural network. So you could see which filters are actually having more effect. That that's really cool. Um, so yeah, Felix, that's the project. Um, any thoughts or questions on that?
No. I think this last part was super interesting. Yeah, because I think that also helps maybe mm, optimizing your training set, things like that. If you want to improve the accuracy, to see like what's the model looking at, and so you can just improve the data that is available to the algorithm.
Yeah.
Yeah, I remember an interesting example, which I think a guy from, I think was a Stanford University professor. I was going through some of the convolutional courses. So the person was describing that the U.S. Air Force, I think, were trying to uh, detect enemy's tanks, and from aerial imagery, and they came up with lots of pictures, and then they trained their model on it. The model was performing super good on the images that they had, like on even on the test set. But when they deployed that thing to the real world, then it completely failed, and they didn't know what went wrong. But later on, techniques like grid came and looking into the internal features and stuff, they they started to realize that the examples images that they collected for training was on a cloudy day, and when they then tested it on other days, that it wasn't, of course, cloudy days on the other days, so it completely failed. So it would be better if you, just like Felix described, it would be better if you know what the model is doing, and then you can come up with data sets which would be more fruitful for the model to be trained on, and then it would be a good exercise.
Yeah, yeah. I saw a similar example, but for like weights, like for weightlifting, like dumbbells and stuff. And then if you check for what it's actually paying attention to, it was mostly like the arms holding something. So if you would show it a dumbbell just like without any body parts, then it would fail to recognize it. Yeah.
Interesting. Interesting. Cool. Well, that's it for today. Um, we'll meet again on Thursday. No, Monday. We'll meet again on Monday, and we'll go over projects that people have done. So feel free to work on whatever interests you.
Thanks, James. Thanks, Navid.
Thank you. See you then.
All
Bye.
right. See you soon.